introduction. Hi, my name is Jason Kim from Quantum Science and Technology Group at the Jet Propulsion Laboratory on the NASA. Today I'm excited to share with you our progress and also challenges, and we discuss some of the challenges about developing atomic interferometer for making a miniaturized accelerometer that can enhance the precise orbit determination or tracking the satellite. So in space, detecting small acceleration or drag is critical because this can lead some kind of problem, like we don't really know the trajectory of the satellite or making some kind of trouble for scientific mission. So one of the famous example is Pioneer anomaly. So in 1980, scientists noticed something very strange. They launched the Pioneer 10 and I think 11, and they were decelerating a little bit, very tiny little bit. It's about 1 kilometer per hour over the 10 years of timeline. So they tried to figure out why this small deceleration was some trouble, and then about 30 years, they proposed 100 different papers talking about maybe expansion of the space-time, dark matter, or unknown planets. So they were trouble about what's going on. And later, by careful modeling, they found out that this was because of some local portion of the satellite was heating it up a little bit more, emitting photons, pushing the satellite. So there's a photon is pushing the satellite a little bit, such that it create this anomaly. So those acceleration was very tiny, 10 to the minus 10 level. So in space, it's very important to measure and detecting this small acceleration for the careful understanding of the trajectory and scientific mission. So because of that, there's already demonstrated some of the accelerometer on the board. So in this mission is in 2018, it's written here, Bepi-Colombo mission by the ESA and JAXA, where they launched the satellite to the Mercury and they put the accelerometer on board. So they put the mechanical accelerometer, which have a great sensitivity. They have like 10 to the minus 8 or 9 level of the accelerometer, and they can measure the acceleration caused by the solar radiation from the sun, and then also Mercury's infrared radiation. So they can push the satellite because of this photon radiation. So they want to put this satellite to measure those kind of acceleration, drag, such that they can understand the determination of the orbit. So then this will help us to understand more about the Mercury's composition, intercomposition, and also some of the information of the surface. However, by comparison, if you try to measure like Pioneer anomaly, level of -10, since it's mechanical sensor, it have a very short stability. It doesn't really measure even though you spend longer time. However, so that's why we need to have a little bit like longer stable sensor and also better sensor. I don't want to say because there's some people working on the Italian other sensors. So there is an interest to develop the good accelerometer, and one of the application can be the precise orbit determination. So for example, right now when we try to understand determining the orbit, we use the radio signal to communicate the satellite, and then looking at the Doppler shift to understand how fast they are moving or where they are. But the problem is that since they are going through the ground to satellite, they pass through the atmosphere. And this atmosphere have a random fluctuation such that this change the uncertainty, create some kind of uncertainty. And this is about the level of 10 to the minus 8. I'm just doing the number. But so that's why we want to make some accelerometer that can capture those kind of fluctuation, -8 level, then we can actually start enhancing this orbit determination more than just radio link signal. So this leads us to look at the quantum accelerometer, because we need to long stable accelerometer and also have a precise accelerometer. And quantum system can give you the good sensitivity. This is how the quantum accelerator works. So first, we prepare the atom in the vacuum chamber. So we cool it down the atom using the laser and magnetic field to try to cool it down and like a cold atom. So then this make a small cloud inside of the chamber, and we can capture it. And then we can cool it down to the about 10 microkelvin or millions of atoms. So it's not single atom, but millions of atoms are cool it down and put it inside of the chamber. So when you turn it up the light, this work as a free mass, so it starts falling down with the gravity. So we can prepare this system, and you can see that there's no cryogenic system, so just a laser magnetic field, and this can work inside of the vacuum chamber, so they just fall because of the acceleration of gravity. So once we create this mass, test mass, then we will measure the acceleration using the interferometer technique. A lot of people will know the light interferometer, but we are using the atom interferometer. We don't need to go to other detail. You can just think that using the interferometer technique to measure the phase shift due to the acceleration. And then at the end, we will extract this phase shift by the fluorescence. We shine the light, and then light is coming out. And this light will be depend on the transition and then how much phase shift it experienced during this interrogation. So if they pick up any acceleration, then we can measure by the fluorescence at the end. So in the whole system, there is no mechanical part, so that's why we can have a long-term stability, and since we are using the atomic transition, this have a good precision, we can have a good acceleration sensor. So our target is to try to make it about 10 to the minus 8, which is where the radio link signal have an error. And in space or in ground, we can also have a long acceleration, but we want to have 100 milliseconds because it will be on the space. So then we can have a long interrogation time because mass will not fall down, it will be just stay inside of the vacuum chamber. And we want to have about millions of atoms with the 10 microkelvin. It's all come from the calculation. So, but there's a problem, and I will mainly talk about the problem of this talk. So we have two main challenges. One is the microgravity challenges, and the other one is the miniaturization challenges. So first one is in the microgravity, it's very different with the on the ground, because on ground we have a gravity. So when atom is when you start doing the interferometer, atoms start falling down, and there's a direction. So then we can use that direction to choose which interferometer we want to do. Either interferometer is going down or going up. But in microgravity, there's no gravity, so atom does not see the direction. So it starts doing all the possible direction, and then the interferometer is really hard to do because now we cannot really know where they experience the phase shift, and it's hard to extract the information of the acceleration. So that's why this actually creates a problem. And some people, I will talk about the next slide. Some of the method, they just use this kind of multi-splitting method and then just extract the acceleration. However, they were not able to give a good sensitivity or good contrast. So we can use it in theory, but in practical, we cannot really use that to make a 10 to the minus 8 level. So we need to find some other way to break this, try to solve the degeneracy issue, so this splitting issue. So one of the ways is creating actual velocity or effective velocity, or the other way is try to filter some of the transitions such that it only pushes to the one direction. And I will talk about the three different things, but the last one, magnetic sensitive one, since they will be sensitive for the magnetic field, which means that they will be picking up the magnetics, it becomes more like a magnetic sensor. We don't want to use this magnetic sensitive transition, so even though there's a method, we will not talk about this method. So one of the ways is instead of falling down, we actually create the velocity itself. So we use the piezometer to actually push the atom, push the meter fast enough, like a gravity, then actually we can break the degeneracy. However, now this requires very precise movement of the meter, and also we need a very precise tracking of the meter. So velocity and position have to be precisely tracked and then controlled. We found some of the piezo which can do, but we just received it, so we will test further and then hopefully discuss more later. And another way is chirping the frequency really fast. So if you chirp the frequency, change the frequency really fast of the laser, then this retracting light will have a small delay because of the distance from this atom to the meter. So then this delay creates a difference frequency between the top and the bottom. And this can make an effective velocity atom experience. So this actually can break the degeneracy, so it doesn't go up, so it doesn't go down. So we can also control that. This work has been published not from our group, from I think French group. And then we also do some internal calculation, and we found that we can actually improve it by chirping the other direction. And then another approach is using some kind of filtering of the polarization. So instead of preparing the two light with the same polarization, we can prepare the light into vertically or cross-polarized light, and then we can filter one of the polarization to fix the one of the direction. So in this case, we are just filtering the light to create the directionality, so we don't really have any active control of anything. But the problem is that now in this case, this co-propagating light can create another transition of the atom, which can do another population transfer, become an error source. So to prevent this one, we need to prepare this polarization really high extinction ratio, and also all the optics have to be really careful. So that's challenges, and then about typical fiber, 18 dB, is create about 1% of the effect. So at the end, sensitivity will be kind of get worse. So we need to have a much better than 18 dB. So another challenges that I'm going to talk about is the miniaturization. So chamber and everything is quite huge. I think typical accelerometer will be like, commercial one will be like size of this, like this box, or maybe smaller. But so then we need to make it smaller to put it into the satellite. So previous work from our group was demonstrate miniaturizing the sensor a little bit, such that this is entire size of the atomic package, and of course laser and computer is in the other side. We don't show it, but it's about this size. And as you can see that it's size of the water bottle. I mean, couple of water bottles. So we tried to miniaturize it, and previous work was demonstrated with a single laser light to do miniaturization of the sensor, and then was able to demonstrate this sensing the acceleration. So we want to do it better. To do that, we have to think about many different systems, because we have electronics, and we also have a laser, and we also have a vacuum. So we need to miniaturize every three components to make a small accelerometer. So first one, you can see that electronic system, we found some commercial PCB board electronic. So this can have a measurement, and this can have deck cars controlling the electronics. When you open it up, you can see there's a lot of room here. So with for the engineering that might not be done by me, hopefully they can miniaturize this part smaller. So that's not something we are worrying about. But since PCB board is already small enough, with considering this size, we can still make it smaller. And we are aiming the total size will be about 7 liter, which is about kind of half of the shoebox. And the other system is laser optics. So a lot of people do the preparation of the cold atom and then interferometer separately, which create a lot of, actually make it size really large, because the collimator for the cooling and then the Raman, that will just increase the size. So what we want to do is, instead of doing separate method, we can try to do it in the retroreflecting beam. But the problem is that this creates another element that we need to do with the LCBR. And we can also miniaturize kind of compacting by get rid of this LCBR and just put the lambda by 4, but prepare the light with the cross-polarized light. In this case, we can have a mod cooling down the beam, but also this can also work as a interferometer when you use the circular polarization. So we are thinking about preparing this way, and that's here's a showing here. So this is a laser system. We will prepare the vertical light coming to the PBS, and then using the many switches to control the either cooling beam and interferometer beam. And then at the end, this will go to the interferometer here, so then we can cool and then do the interferometer. In this case, we are not using the LCBR, which can reduce the power consumption by 5 watts, because we want to do 3 axis interferometers, so 3 LCBR, then size can be miniaturized, and also power can be reduced. And so this is kind of example how we are miniaturizing it. Of course, at the end, it will be much better with the better engineering. So we are just buying some off-the-shelf component like PCB mount for the laser optics and then PID system. So this is kind of typical experimental laser locking configuration, where you have a optic system and laser lock box, frequency, and then laser driver. This whole thing can be miniaturized to this level, where then we put all the locking electronic and the laser mount is on in this small size. Of course, this is still big. We want to make it miniaturize it. So that work, right now we are just more like a proof of concept. Once we show that this is working, then we will further miniaturize by working with the companies. So another last part is actually the vacuum part, because vacuum is quite difficult. So usually when you think about the vacuum, we have an ion pump and we have a turbo pump. And if we can detach this vacuum, then we can actually make a size really miniaturized. So previously, people show that pinching up the vacuum to hold the vacuum inside the small chamber. What do you mean by the pinching up is more like when you're thinking about the balloon, you can make a balloon and then just tie it. Then the pressure keep inside of the balloon. Similarly, we can suck all the gas out and tie it. Then hopefully this will stay vacuum inside. So this technique has been demonstrated with the NIST and our group, where they make a clock. So they capture the mercury atom or strontium atom inside of this pinch-up tube, and then they were able to stay low vacuum, and then they were able to do the clock measuring the time using this one. So about years or 100 days, they were able to show that atom is still there with the low pressure. So we want to leverage the previous technology and try to adapt to our interferometer or accelerometer. So we are also trying that, but we fail many times right now. So first try, we tried to pinch up, but we found that there is a leak on the chamber. So we kind of pinch up and then we made a mark. We made a mark and pinch up and we don't see the mark. So that's kind of first failure. But we are trying for the second demonstration. We prepare another chamber and bake it and then prepare another mark. And we saw the mark, and this is the whole size of the interferometer. We don't have an interferometer yet, but this is the whole size of the mark right now. And we believe that it will be bigger than this size. And it's more like proof of concept again. And it's like size of the water bottle right now. But for the engineering, we believe that we can miniaturize it for smaller, such that maybe like one of the coffee cup size. That's what we are aiming for. So you can see that there's many challenges and many problems we are solving. So we need definitely a lot of help from everybody. So we don't really, if anyone knows the piezo, or if anyone knows the optics, or vacuum system, or electronics, I'm happy to talk with. And good physicists, we also need a good physicist too. So thank you so much, and I'm happy to answer any question.
Yeah, thank you very much for this very nice talk. Are there any questions? Yes, please.
Thank you for the nice talk. A quick question. So you mentioned 10 to the minus 10 in your first slide.
Yes.
But you are aiming at 10 to the minus 8. So
yeah.
Do you expect you can go below 10 to the minus 8?
Yeah.
This?
I think getting a -8 is very challenging too. And if we make an interferometer with -8, then yes, we can make it to 10, because maybe about 10 minutes of the averaging, we can reach to -10. So we are not worrying about that part, but getting an 8 is actually very challenging. So in theory, it should work, but in practice, it's not. So we will make sure to work on the practice and then make it work.
Thank you. There was another question there. Yep.
Hello, very nice talk. And as we discussed in Monday, and I just wonder now how to measure the angular velocity of the atom, because now we always measure the linear accelerations, maybe from just along the laser directions. So
yes. So in this configuration, it's hard to measure the acceleration, but there is another configuration with they can measure the angular velocity. So that's called the quantum gyroscope or atomic gyroscope. It's just a different configuration, but we can do the same thing with the different physics. I mean, not different physics, but yeah, interferometer technique.
So the output measurement is angle or angular velocity or angle. Okay, thank you.
Okay. One quick question back there.
Thank you for your talk, and I got a very silly question for you. So, it just sounds like your sensor is super sensitive, and probably the most sensitive accelerometer.
I will not call that,
but anyways, then is there any reference acceleration kind of a source that can generate like small acceleration, like 10 to the negative 10 or something like that? So, for example, you're building a sensor, making up a sensor, and
so how
to
do we
sense
measure
such a small acceleration, you need to create a very controlled acceleration. So, typically, what you do for that?
So in ground, we just gravity is there's a gravity, so we can just measure the gravity to say it's the good level, I think. But In microgravity, we can either do it in the drop tower or we can do it in the airplane. People have demonstrated the drop tower and airplane to show that they can go down to like zero gravity, like zero measuring the
So
zero.
like your aim is to make as close to zero.
Yeah.
Ah, okay.
Yeah, we have to